Hi everyone, thanks for joining us today in today's Adapt Builder webinar. We appreciate everyone's attendance. This is actually the last webinar we're going to conduct for general builder usage this year. There will be other webinars as we introduce Adapt Builder 2019 and new features moving forward. But this is the last of this particular series. We do have one webinar that we're going to reschedule, which is relative to punching shear. We decided to reschedule that webinar due to some modifications we're making in version 2019. So we're going to cover those since that version is close to release. It's the tentative release date is August of this year. So today's webinar is being recorded, and we have we'll put this up on the webinar playlist on our YouTube channel. Today's webinar will mainly focus on the functionality of tendon modeling and being able to modify some of the modification tools relative to tendons for their inclusion in slabs and beams in Adapt Builder. And there's a few main highlights that we're going to look at today. We're going to look at how do we input tendons both manually and by mapping. Usually it's a combination of both within the software. We'll talk about and define straight versus spline tendons. What does that mean in the software? It's really just the way that the tendons are modeled. We're going to look at how do we display different characteristics of a tendon, and what those display options, where we set those display options, how we modify tendons, etc. We'll go into tendon mapping, both banded versus distributed, what to watch out for with tendon mapping, and then we're going to talk about modification through individual tendon properties and through the Tendon Editor, which is a more rapid way of being able to modify tendon properties, and then we'll go into the Tendon Optimizer. So we're going to do this individually, kind of piecemeal these different aspects of tendon modeling and design together. Today's session should last roughly an hour with Q&A at the end. So if you do have questions, just feel free to enter those into the chat box, and we'll go ahead and get started. So I'm actually going to start by defining the straight versus spline tendons, and we'll go back and look at manual versus tendon input. So we're going to kind of jump around these few different points, where the Tendon Optimizer will be on the back end of the session. So we have two models we're working with. We have a model that really is just a full model. This already has tendons built within it, and then we're going to start looking at a model without the same model without tendons. So if you've ever used Adapt PTRC, our 2D strip program, that program is nice because you go through a linear wizard and you enter all of your input data, and that program will optimize or provide you a result for the total force and also the profile of the cable. What are the different control points for the cable? So that's a very direct way of designing post-tensioning. I think what happens with PTRC, the slowdown might be being able to take an actual, two-way continuous plate and breaking that up into strips that then have to be modeled in that 2D environment. So Builder is different than PTRC. Builder, we model the plate. In this case, we have a two-way slab, and in order for us to actually check the stresses in the slab and check the pertinent serviceability and strength requirements as it relates to a post-tension design, we have to enter the post-tensioning. So the entry of the post-tensioning becomes a modeling exercise where somehow the tendons have to get into the model. And unlike PTRC, where that program designs the PT, this program, we model the PT and then we check and make sure our stresses, our pre-compression, our balance loading is acceptable, or if it's not acceptable, we have to make modifications to the to the post-tensioning in order to design that system within an acceptable range. So there's different, fundamentally there's just a difference in how we approach tendons and post-tensioning or pre-stressing between both programs. So one of the most challenging things, I think, having dealt with users over the past 10 years is being able to model the post-tensioning, number one. What are the steps needed to just model PT, and then how do we model the PT? How should it be laid out? Where do the banded tendons go? Where do the uniform tendons go? And that oftentimes just comes with experience in PT design. So we're gonna focus more on the modeling aspect of the PT and just some of the different assumptions that you want to be aware of as you're modeling post-tensioning. So I'll start in this blank model today. We're going to take a look at, we're going to mainly be using the tendon ribbon. Now this ribbon only becomes active if you've entered the program in the PTRC scope. So if you enter an RC scope, you won't see this ribbon. You'll want to close the program and reopen it and have the allowance of using these different tools. So when we model post-tensioning, we have this notion of a straight tendon versus a spline tendon. A spline tendon just allows us to model the curvature of the cable as it might truly be represented in the physical, construction of that particular cable or placement of the cable. A linearized cable is more of a idealized segmented cable that might be just easier to model. The program accounts for the true length of the cable when it calculates losses. So when we calculate the friction and the elongation, it accounts for whether that tendon is linearized or whether it's spline. Spline will give you likely more accuracy based on a comparison with the actual as-built condition of the tendon. So to illustrate the different differences here, I'm just going to assume in this model that we're going to put, let's say, banded tendons in this direction and then uniform in this direction. And I'll just model, let's say, a banded tendon on this line right here. Now, if a tendon is completely, let's say, orthogonal or straight, there's no in-plane deviation, then using a spline doesn't really make sense. It's easier to just model a linearized tendon. Spline tendons do have their, they have their negative side too. They can affect and slow down certain aspects of the program. For example, when we generate design cuts, design sections, and we want to pull up the design section properties, the program takes longer to generate that idealized section data when it's a spline tendon versus linearized. So our recommendation is use linearized tendons where you can and only use spline tendons where they're necessary. That's what we would recommend. So here we're going to just take and add a tendon. This is manual modification or manual input of a cable. And we're going to select a cable. I recommend when you're drawing cables, don't flip-flop the direction. You can flip-flop the live and dead end if you need to, if it's stressed only from one end. But if you model from bottom up and then top down, and you go into the input or the tendon properties dialog window, the dialog window is always based on first point to last point. And if your first point is here on the top or at the right and to left, then you're going to likely become confused. It takes a little time to get used to when everything is flip-flopped. So here I'm going to model from the bottom up, and I'll start down here. I'll just start, there's a tiny cantilever. I'm just going to skip over that and go to this first column. And when we're modeling tendons, linearized tendons, a lot of times we'll use the orthogonal mode. And rather than zoom in as close as we can to the support, we can just zoom out. It doesn't have to be exactly perfect centered on the column. If we zoom out slightly, we can typically model this a little bit easier than zooming in and out and more, more quickly. So I'll go ahead and snap this to this edge of slab. Okay, and that's tendon 1. Tendon 1 is represented just as a linear tendon by one line. Let's say this is just a polyline. It has properties associated with it. It's actually an internal element once it gets discretized to the shells and to the frame elements. So there's a few characteristics graphically that represent what's happening with the tendon. The program has control points and just static points that are not you don't have the ability to modify them graphically here. The control points will always match the color of the tendon. So for example, this endpoint, the start and end point, are always control points. They are the anchor points. The interior snap points are the high points. So the snap point here, you can see this is a red symbolic dot there. The same thing here at the columns. I could select this and I can move these points. When I move this horizontally, this is linearized. You can see there's two spans and then a span here, and there's no horizontal curvature to this cable. It's completely linearized. If we double click on the cable, we have characteristics that belong to that particular tendon. There's the area of the strand. Here we're going to assume we're using 1/2 inch diameter 7-wire strand, 12.7 millimeters diameter if we're using metric. The tendon height, or the diameter of the tendon, is 1/2 inch. This is actually the area, 0.153. This is a 1/2 inch diameter cable. And we specify the number of strands. This is not the individual strands that make up the 1/2 inch diameter. This is really just the number of tendons that we're representing by this one line. So for a banded system, you might have, let's say, one cable that equals 12 strands. You might have two cables that each equal 6 strands. There's different ways to model that. You can model one cable that equals 1 strand and do 12 of those. So that's taking it to the extreme. The more broken out the number of cables you have, the better control, or let's say the more accurate the deflection in the program. So if you're trying to get the most accurate review and, let's say, result for deflection, and it's very, very sensitive, you might actually take banded cables and break them out individually versus representing them as a lump value of strands like so. Now in this general tab, we also have the mode, and here this is straight line mode. Notice if it's straight line mode, everything below this is disabled. There's no first or last end anchorage inputs or parameters for the cable. This cable is represented by either calculated force method or effective force method. If it's effective force method, if I was to draw just a graph here, this is a force graph for the cable. We might say, in reality, if, let's assume we're going to, this is the dead end and the live end is up here. So the loss diagram might look like this for this cable. This is the short-term loss, the friction loss. So if we have anchor set, where we have anchor draw-in at the anchor, then we get some type of inflection that looks like this. So we build up to this high point over some distance we'll call x, and then we get loss over the length of the cable. So this is the actual diagram for the force, and we're just going to assume that our effective force is somewhere in here. It's just the average of this set of numerical values along the length of the cable. And then we also have to offset this number. This is just a flat line. We have to offset that for long-term loss. So this delta here, which is constant along the length, is just the long-term loss that we assume as part of our effective force value. So the program will give two options. You can specify a cable as effective force, which means that the first and live end don't really matter numerically or analytically in the model. They might just be there for representation. So if we want to represent where we want the stressing ends, then we could use this. We'll say that this is live dead. This starts at the first point. The last end is the last point. So here we have live dead. Our effective force, we're assuming, is 26.5 kips. The default, by the way, is different. It's 26.7, which is 175 KSI. That's ADAPT's assumed effective stress times the area of the cable, which is 26.7. This particular model, we rounded back down to 26.5. If you go to calculated force, then we have a few different input parameters. We have to specify the draw-in, the seating loss. We have to specify the jacking stress or the jacking force given or stress given. So there's different ways to represent the force when we stress the cable. And also we have to enter lump sum long-term loss. So we assume a long-term loss. As a side note, the next version of the program will actually calculate long-term loss explicitly for unbonded systems. So that's coming in 2019. You'll no longer have to, if you're using calculator, you'll no longer have to use this assumption. And it's based on the code in ADAPT Felt, which is used pretty extensively for loss calculations. One thing also, if we use calculated force, you'll notice in the shape, I'm going to skip over location for a minute, in the shape system friction where we define the profile of the cable and the different shapes of each span, there's this option that says force diagram. And this force diagram is actually turned off if you don't have the PT shop module enabled. So what this allows you to do is this allows you to see the loss, and it calculates it without having to actually analyze the cable. Prior to analyzing, you can actually see the loss diagram. So if I was to close this instance of the program, I'm going to go ahead and just reopen. Let's see, make sure I minimize those windows. I'll reopen Builder, and we will reopen with the PT Shop module. Okay, so if you've ever wondered, well, what's this button for that's always grayed out, you have to have the shop module to open it. And if we go back into that model, look at this cable, the stressing is set to calculated force. I can now come over here and select the force diagram, and this shows me the loss of the cable. So if you have, again, a very sensitive system, maybe a beam system where you have to have more control over the actual losses for the purpose of not only the serviceability but also the strength, because the strength is affected by the final force in the cable, then you may want to go this route and base maybe the effective force off of this diagram, or just use the direct calculated force method in the program. You do not have to have the shop module to actually use the calculated force option. This just gives you the ability to see that up front before you analyze. So we're going to use effective force. Location really just gives you the coordinates and the position. Where is the tendon referenced? Well, this tendon is located at the reference plane called current plane. That's where the profile is established from, and also the XY coordinates. If you wanted to manually or by coordinate adjust the position of the cable, you could use these coordinates instead of using the graphical pick and move method for modeling a tendon. Graphically, it's probably easier than dealing with coordinates, but that's available to you. You do not need to worry about offsetting tendons. The tendon offset is typically done based on the CG, these values in this table under the Shape System Friction tab, and it's always referencing the slab or beam that is modeled or referenced from the same plane. So if this slab was actually referenced, if I push this slab down, you can see this slab is 7 inches thick. The location is 0. That means it's the top of the slab is at the reference plane. If I move this slab down 4 inches, so there's a 4-inch offset. If I look at this slab and turn on the reference planes, let's go back over to visibility and view settings. You can see there's a 4-inch gap between the current plane and the top of slab. Looking at that tendon is auto adjusted to be within the slab that it's referenced from. So the tendon itself, you can see, is still within the thickness of the concrete, and the location is still set to 0, but again, it's referenced off of the concrete. So you do not need to touch location for post-tension cables. Go back and reset that to 0. One thing to note here also is the uplift. This image gives a lot of different information, the span length, obviously a view of the profile of the cable relative to the CG. So at the midspan, for a default reverse parabolic shape, the CG is set to 0.5 times the span length. The inflection point, if this is if it's reverse instead of simple, the inflection points are 1/10 of the span length from either end. So those can be modified. Those are just the defaults. The midpoint is always referenced from bottom up. The support point is referenced from top down. Okay, that's important because we're going to go into the Tendon Editor and show you when we edit tendons on plan view, it is the CGs that you see there are set up similar to here. Top down at support, bottom up at midspan, and top down at anchor. So that's shown by these little blue lines that we see connecting the surface to the tendon. The uplift for the cable, this is used only in one location analytically or result wise in the program. When we use balance, when we check balance loading, there's a new method that came out in version 2018. It's called Simplified balance loading. That particular method uses this uplift value. This is the average uplift based on the cable profile and the force in the cable. This can be calculated without need of finite elements. You can just calculate it based on the geometry and the force. And we use this number when we calculate the uplift for the simplified method. So if there's 12 strands and there's 3 of these, let's say 3 of these bundles, there's a total of 3 times, let's say 1.32, and we use that as the uplift and we compare it to the dead load, the sum of the dead load applied in the span, and we use that to produce the balance loading. So that's different than the balance loading check using finite elements. If we go over to analysis, I'll show you what I'm referring to here. This one, let me go over to this one. I'll turn the tendons off in view. Let me go to the results. So under design section results, you can see for balance loading there's 2 methods. Balance loading FEM, which is really a sum of the vertical force components due to the post-tensioning in the span, and that means that summation could be influenced by tendons in both directions, not just one direction. And then there's simplified. So if we look at a, let's take this span right here. When we use simplified method, we only consider the tendons actually cutting these sections. We take no effect, or the tendons in this direction have 0 impact on the balance loading when we use simplified. Technically, these could have impact on the balance loading when we use FEM, because you can, if the profile of this banded cable, for example, is something like this, once you get beyond that inflection point, you have some level of uplift, let's say, and downward here. So the net effect based on the force in these nodes within this tributary could be impacted by these banded cables. That's what happens with FEM. So wanted to point that out. We'll go back over here. Okay, one thing to note in older versions of the program, this was primarily where we would modify cables. And when you have 100 cables in the model, it became time consuming. So we've introduced new options in the Tendon Editor that allow you to more rapidly modify cables. And I'll show some of those options. I'll define them here in a little while. But I wanted to just close up the loop here. The FVM option allows us to consider or ignore tendons. If we set this to disregard, then when we analyze, the tendon is not considered. It's as if it's not in the model. Properties just define the layer properties for the tendon. Whenever you're modeling tendons manually, let's assume that this is a uniform cable. You want to make sure you set up the uniform cable with the proper inputs, the proper profile, the number of strands, the right diameter, and so on, before you go and you replicate it 20 times. Otherwise, you're going to end up having to modify those cables. So be aware of the properties that you're setting up here. The shape, there's different shapes you can use. There's several different shapes. Reverse parabolic, partial, these are the most commonly used in, let's say, interior spans. On cantilevers, we have cantilever up, partial, harped, cantilever down. The cantilever down is the most common on true cantilevers, or straight. You might just go from high point straight down to low point. Those yield fairly close solutions. They're not too different, and if you look at the equivalent loading or the balanced loading from those shapes. And then extended reverse parabolic. This last shape is primarily used for adapt slab on ground, where we have ribs in a post-tensioned slab on ground, and we have to control the stresses due to edge lift, where the soil pushes the edges of the slab upward. So most common to elevated slabs would be reverse parabolic, partial, and then the cantilever shapes where we have cantilevers. For transfer beams, we have options harped that might be useful for transfers. You might say, well, where's the simple parabola? Well, simple is just established by setting the x1 and x2, or excuse me, x1 and x3 values to 0. So you basically eliminate the inflection point and you end up with a simple parabola. If you're wondering about these values here that define the points along the span, you can always click on this button. That will show you an image and give you the values and the limits of the values for the specific shape. Okay, so one common thing that we see quite often in tendon modeling is a shortcut that users sometimes take that ends up affecting the strength calculations, and they end up getting more rebar than what's required, a lot more, and it ends up in support. So one thing you want to avoid is, if you're going to set this number to 1 and you say you change the effective force, I'll change this back to 575. If you use this method, you have to also increase the area. You cannot leave the area to 0.153, because the calculation of the nominal stress in the cable at strength level is affected by these values. So if you're using the method of always leaving the number of strands to 1 but modifying the force, you need to scale up or down the area per strand. If this represents 30 strands, you need to multiply 0.153 times 30 and enter it here. Okay, our recommendation is leave the effective force as is, and if you do that, you only have to modify one value, which is number of strands. And this can be decimal input. It does not have to be whole number input. It can be decimal. So our recommendation, again, area of strand remains constant, the effective force remains constant, and the only number you worry about is number of strands. If you choose to set this to 1 always, then you have to worry about 2 numbers to modify. Okay, so that's something that We see a lot of questions about that and results related to that. Just make sure that you follow those guidelines if you're using that method. So that's a linear tendon. Nothing crazy about that. Now we go to spline. And when we change this to spline, we get first and last end options active. Okay, this allows us to set the angle at which the anchor connects to the slab edge. Right now it's 90 degrees. So for example, if I look at this, you can see this has curvature now applied to it, and this is based on some shape function for this spline. If we go and we change the location of the slab, if I move the slab, in earlier versions this tendon would move with it. We actually disabled that because it was causing some crashing problems with tendons, and you can still extend the tendon back to the slab edge. So if we go back to tendon and we use trim extend, when I do that, notice that this actually comes back in at an angle, at a 90-degree angle. I could change that angle. Maybe I want it to be 60, negative 60, 45, and so on. So we have different options here for fixity of the tendon to the slab edge. If I go 60 degrees, and this is actually the last end, I'll change last to 60. Notice when I change that, it automatically updates the tendon and its anchorage to the slab. If I move that slab out again, let me move it out a little further, and I say trim and extend this cable, nothing happens. Okay, this distance between the slab and the tendon is too far. It's greater than a threshold. So under tendon settings, we can increase the tolerance for trim extend. I'll say that this is going to be 6 feet. And I'll go ahead and trim extend that again. Okay, and that might be still too short. Let me say 12. And now it trims and extends. So there's ways to control the trim extend in the tendon settings. But just be mindful of the anchorage setting. By default, it's 90 degrees. If you don't want an anchorage setting and you just want the tendon to follow the shape function for the spline, you can set the tendon to free in the first and last end options here. Normally there's more than one tendon in the slab, so if I copy this tendon, I'm just using Control Paste. Notice when I do this, it auto trims back to the slab. Like here, it's off the slab. When I click it, it goes back and connects to the slab. So that's something that you may not have seen before. If I wanted to change all of these to free at once, I could use the Tendon Editor. So I'll go into Tendon Editor, and this allows me to make more changes globally than just for single tendons. So I'll go over here to anchors. We might want to change the anchor to free, and I can then just window select the tendons I want to change, and it circles the tendons that were modified. Okay, so if you ever see this little yellow kind of square or circle at the end of a tendon, that means that's a modifiable point for the particular mode that you're in when you're in Dynamic Editor. If I want to change the CG for any number, now these numbers are really small, so I'm going to just pause this, go into the visibility, and under finite element for font size, I'll change that to 15, and for symbol size, I'll go up to 5. Okay, and I'll resume that, and now I have readable values for the control points, and I can make changes here globally again. So maybe I want to change these to 4. That's too much. It's a 7-inch slab. Let's say 2, and I can just window select my points like so. Or you can just click on one point. I could go in and just click on that point and change these like so. There are also options for end span shapes. So if we have an end span that we want to modify, this span on the end here is actually from, let's see, Yeah, this span is from here to here. Is that right? No, let me back up here. From there to there. So if I change that span, it's not really a cantilever. This is because I didn't model the cantilever here. I moved this slab out, and this was originally just a reverse parabola on the last span. Let's assume it's a cantilever. So we'll go ahead and just select those, and that changes those to cantilever down. Okay, so there's different ways to make changes other than inputting the changes per tendon. You can also go to trim. If I take this, let me pause this again. If I take the slab edge and even push it out further, and I use this trim option, I'll resume. Then I just window select, and that trims. I might want the shape to be set back to, or the anchor to be set back to free on that side, or let's say 90. That modifies the anchor. Force, you can modify the number of strands or the effective force, and this will write the number of strands when we go into that mode. It will write these at the start point of the cable. So here I can select number of strands or effective force, and that changes the effective force. It just changes it based on the mode that you're working in. And then mode, if I wanted to change all of these tendons to spline, or from spline to straight line, I could, again, just switch this. Now they're all linearized. Maybe I want to make a couple of them spline. Oops, let me try that one more time. Those were previously selected. Okay, and I'll go back to spline, and those two are now spline. So this is where most of the global changes occur in tendon modeling, is within the dynamic editor. Doesn't mean you can't do it individually, but this is a pretty useful tool for making changes to tendons. Let me just see if there are any questions that have come up here. Looks like no questions. Okay. Adding points to tendons, and I bring up some of these comments for users who have used the program historically in much older versions. There's some things here that are pretty different than how things were in the past with modeling cables. So if I wanted to add a span, let's say here we have a linear tendon. There's an anchor point right there. There's another control point here. This is a cantilever down shape, and so I might want to add a span between point 1 and point 2. In previous versions of the software, if we went into this tendon and we wanted to add a span, we would have to go into the shape system friction, and we would add a span or delete a span from the first span location or the last span location. So adding interior spans was a little bit painful. You had to add a span and then graphically go in and modify the points, and you could only really do that through this dialog. Here we can right click. Let me go back and make sure that's selected. We're going to take this tendon, right click, and we're just going to insert a point, and that inserts a modifiable point for the cable. So you can see this here. I now have a anchor point. This is a control point here. I can move that. This is actually the cantilever down shape, and then I've added this span here where we have a control point at this location also, and this is a reverse parabolic shape. By default, it's reverse parabolic when we add the span, and you could add spans using that option. Right click, insert, or delete a vertex. Here I'll delete this one, and that goes back to the original shape. If you have a situation where you have openings, maybe let's go ahead and put an opening. I'm going to model an opening right there. Try that one more time. Enter instead of escape. Now here I want to keep the control points. I want this to be my high point. I'll circle these also. So this is high point. The other high point is down here, and this is the low point. This is LP right there. I want to maintain these high and low points, but I want this tendon to just swerve around the opening. So how do I control the in-plane maneuverability of the cable? There is a question. Let me go ahead and answer that. The question is, how can we change the default view of tendons? They want to. I want to view the dead and live end in the default view. So I'll get to that here in a moment, Miriam. Right after we talk about swerve tendons, we'll talk about tendon display options. So give me just one sec, and I'll get to that point. So to swerve this tendon, I'm going to, under the tendon toolbar, I can use the option to insert a swerve point, which allows me to control the in-plane deviation or curvature of the cable. I can insert or delete a swerve point. Here I want to insert, so I can right-click also and say insert swerve point, and I'll add one, let's say here and there. And the symbol for the swerve point is this little double green arrow. If we take that and we move that out, the program lets us modify the shape of that cable using the swerve point. It doesn't change the control points, it just changes the shape of the cable in plane. So if I look at this using the rendering option, I'll turn off the columns and walls, and I'll go ahead and let's scale this vertically by a factor of 5 so we can see the curvature, or hopefully see it. You can see, let's see, I think I have this thing flipped upside down. There we go. Okay, you can see this cable starts at a high point, it drapes down to a low point, but it also deviates in the in-plane direction and comes back up to a high point right there. So these are the tendons currently in the cable and their discretized segments. This is a nice view, by the way. If you ever want to check the modeled profile of cables, you can use this modeling, this rendering option there. Okay, now to the question, how do we change what we're seeing on screen? If we go back to Tendon and we use Display Manager, this allows us to display all sorts of things about tendons. So we can display tendon properties, ID, tendon label, area, system. If I actually turn all of these on and say OK, it's just going to give me a long string of text at the bottom. So this is somewhat abstract. It's tendon ID 34, label tendon 134, number of strands is 12, area per strand 0.15. It's an unbonded cable, and the total length is 138.39. This length that you see is the projected length. If you go and produce the tendon report, in the reports menu, that is the true length. Okay, so you may see a difference between this length and what is reported under tendon report. By projected, this is linear, 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 linear. That's the length that the program calculates by plan. The report is more accurate. So okay, the question is, how do we see the dead and live end? So this is just tendon properties. If we go back to the display manager, let me turn off this stuff here. There's an option to show stressing ends, dead and live. If we turn that on, an arrow means it's a live end, bar means it's a dead end. Okay, so this is the representation of the ends. If we now go to visibility, we'll just show this here. These are not represented in the rendering. Okay, they're only represented in the plan view. So the anchor here looks identical on either end. So they're not represented in this rendering. They're just represented in this view. So how do we make this the default view? Well, whatever you set here is whatever this is now the state of viewing that we're in. This is currently the view state. So if I model another tendon like so, notice it shows me the dead and live ends because that is the current settings that we have that are turned on. So when you say default view, the default is whatever is currently set in the display manager. If I turn the tendons off and on, if I go back and turn the tendons on, it just pulls up whatever is stored in this dialog. Okay, I think that answers those questions. How do we represent force? Well, if it's an effective cable setting, we can have force per strand or total force. So this will show us the setting. This is total versus effective force was I think 26.5. We can also, this is effective force and it actually says F effective there. We can also do calculated force. So if we look at the calculated force, we can represent it by the average force, minimum force, or maximum. These are all set to effective force method. So when I select this, it reverts back to effective force because the setting in the cable is not calculated. It's effective. So here, if I go to calculated force and I come back and I turn that setting back on to average, minimum, or maximum, now you see this is the average force along that cable. And it's much higher because there's 12 strands. This is the summation of the strands and the summation of the force over the length of the cable. This is average. So the only time you see actual individual cable force is if you use effective force method. Okay, if you want to show the control point heights, you can use this option, show the heights of the control points. These will be displayed automatically when you go into the Tendon Editor. However, notice one thing. When I use the display manager, which is really used to export and create a data sheet for the tendons that you're modeling, when I use this manager, this is referenced from high point. You can see, let's see if we can find the high point here. So these are high points. This is 6. This is from the bottom. Everything here is referenced from the bottom up, which is more in tune with how it's represented, let's say, on construction or drawings that you're preparing. So this is 7 inches minus the 1 from top. That gives me the 6. And then this is the bottom midspan. These are just 1 inch from the base of the soffit of the slab. If I go into the editor and I go to CG, this changes. This is 1 inch from the bottom and 1 inch from the top. So the editor is always in tune with how the tendon is represented in this particular individual tendon editor. 1 from the top, 1 from the bottom. Okay, so the display manager just references everything off of the bottom. You can also control inflection points, the shape of the cable, radius of curvature. There's other geometric outputs that you can graphically display. And then the spline curvature, this will show us where we have slopes greater than these different ranges here that might indicate the need of, let's say, hairpins. So around this edge of the slab, we have we have more curvature there, which may indicate we have to put in some hairpins at that particular location. That's only represented when we model spline tendons. The other tendons are left to their default color. These are linearized tendons here. All right, so we've talked about, let me go back and just refresh. We've talked about manual input of tendons, straight versus spline, some display characteristics. And we've talked about modification through the editor. We're going to talk now about mapping and optimizer. So let's go back to this model. I'm going to delete these cables. So the question comes up pretty often: how do we model post-tensioning in the slab, right? I mean, what are the best ways to actually get the tendons in the slab? There's just the old-fashioned way of manual input and then replication, which is probably more useful for uniform cables. And then there's the option for mapping cables. So I'm going to show you mapping of a banded cable. Mapping of banded cables requires that you have support lines established in the model. So here we have we talked last week about support lines. We have our support lines set up, and I'm going to generate the strips for these support lines. I'm just stretching these out because I modified the slab edge earlier. Okay, we're going to go ahead and generate our design strips. And we have strips in the X direction, and then we have strips in the Y direction. We're going to say that the Y direction is the banded tendon direction. So in order for us to manually input these tendons, we might want to manually input them by a couple of different dependencies. One, what is the minimum pre-compression that we're targeting? Let's assume it's 125. So for this particular banded strip right here, I might take the worst case area of the strip, because we have varying areas. We have, let's say, area 1 right here. This might be area 2, area 3, and how am I defining the area? Well, it has a wider width than the other regions. This one tapers, so technically, each step is a different area, and then this bumps out, right here. So we have all these different areas. We're going to just assume for this one they're roughly, close to the same in terms of their width. We'll just take the maximum as a conservative approach. It's not grossly conservative. It's just a way to get the tendons here. So we'll take this area of maybe this section cut. That's 371 inches times 7. And if we take that area and we multiply it by the minimum pre-compression, we need 325 kips of force in this banded line to meet minimum P over A. So we'll take the 325 and we'll divide it by our assumed effective force of 26.5. We need 12 or 13 strands in this strip. So now I have to go back under tendons, add the tendons, assume a CG. I might max out the CGs unless I have very short spans and I know that I'm going to raise the profile so we don't overbalance the load, the dead load in the span. Or I can use the mapping tool, which tries to target pre-compression and balanced loading. So we're going to select this strip. I'll go over here to map banded tendons, and we get this dialog that pops up. We're going to use the design strip width, which is manually what I had just done when I broke this out. I said, okay, we'll look at region 1, 2, 3, 4, 5, 6. We'll base it off of region 1. That's essentially what this does. It actually creates a force necessary to be or for each of the design cuts, and then it envelopes the required force for the cuts. We'll use the design strip width, the pre-compression that we target. Let's assume it's 125 to 300. The percent of the self weight that we want to balance, we'll say, is 50 to 90%. Miriam asked a question: Can we design a PT slab without reaching P over A in the banded direction? It depends on what code you're using. If it's ACI code, technically, no. If it's a PT2A slab, I guess you could say you're only using post-tensioning to control deflections and then design it as an RC slab. But usually the answer to that would be no. For ACI, that's our opinion. For European code, the answer is yes. I mean, there's no hard, fast rule for P over A minimum or maximum for like European code or British code. There's guidelines. I think there's a technical TS43 for the British code, gives some guidelines for pre-compression, but it depends on the code. If you design a design per European code or EC2, you could put whatever tendons you want in the system, and if you're insufficient in terms of the stress, then you're just going to get more reinforcement for crack control. So you might, it's a trade-off. If you add more PT for that design, you'll get less reinforcement for crack control because the post-tensioning is controlling the stress, which might indicate where it's cracked. I mean, those are directly related. So for ACI, usually you meet the minimum P over A both in the banded and in the uniform directions. All right, so just looking to see if there's a follow-up question there. I think we're okay. All right, so we enter our inputs for pre-compression and percent self-weight to balance. We're backing off a little bit for the maximum just because this is a two-way slab and we're going to end up balancing load also in the uniform direction. So placement of the cable, there's ways to have the program represent the banded cables. We can represent it as individual tendons. Let's assume that the program determines we need 12 strands here or 12 cables. The program would model all 12. You would get 12 lines of cables here, which is more time consuming and takes more effort, and it's less efficient because you have to modify more than one cable. You can also represent this on the other extreme end as just one group. So I might have one group of 12. By default, we represent usually two groups, maybe two groups of 6, and we offset those from the support line. People will ask us, well, if you're going to just use two groups, why not just use one? That's fine. Make sure if you do use one, you offset it from the support line because it becomes difficult to snap on the tendon directly if there's a support line right on top, unless you turn off one or the other. So that becomes more of a usability problem than anything. So we'll use two groups with a 1 foot offset, and then we assume an effective force. Okay, so if the required force per this calculation here is 325, we have to divide that by some assumed effective force, which is 26.5 here, and then we would define the shape of the cables. Now the shape is important because when we map tendons to the support line, the tendon actually maps it directly to the spans on the support line. So you can see we have a tiny little span here. This is span 1, or the last or the start span. Everything in between is a mid span, and then the final span is the end span. Okay, and so if we come back and map that, we have first span, which is a cantilever, that's down on the bottom. The mid spans are all going to be reverse, and the last span will be cantilever. If I mistakenly have these all set to reverse, which I'll do just for example, and I map this, you can see there are two tendons that are drawn. And I'm going to go back and turn off my display of effective force. And there's a couple of things that are happening. The program actually flagged one of the tendons because it was outside of the slab. But you'll notice on these end spans, these are actually reverse parabolas. How do I tell that? Well, I could go into the properties of a cable. This is 5 strands times 2, so there's actually a total of 10 strands here. And you can see these these reverse parabola shapes here. So we would either have to modify this inside of this dialog per cable, or this is where the editor becomes useful. We can go to shape. I want this to be cantilever down versus reverse, and I modify that like so very quickly. And I could, if I had multiple tendons, I could very easily go in and grab multiple cables there on other banded lines. We also might want to drop a CG. This is a pretty short span to try and if this is our slab and we have a support here, right now we're trying to take this and come up to a high point and then back down, and this span is pretty short to do that. So we actually might want to just drape this straight across then down into our profile. In that case, we would use the CG value, and we're going to use a 3.5 value, and I could just quickly edit these CGs on these. This is a more of a longer cantilever, so that one we might actually want to leave to like 1 or 2. There's another question. Yes, Marcos, if usually the more tendons you have, like if you model and distribute all the cables, you're going to get an improvement in the accuracy for deflection. Unless the deflection is right, if it's really sensitive and you're trying to get the most accurate representations so that you can justify, the amount of displacement relative to a criteria, then you may have to transition to multiple cables versus lumping them like we're doing here. Okay, so that's a banded cable example mapping. Notice this cable is out of the slab. Because we mapped to 2 sides, one cable is actually short of the slab. Remember, it's mapping it off of this point in the orthogonal direction. That means if this slab edge is sloping, one of them is short this way, one of them is long this way. So that's easy to rectify if we just simply grab the cables, just select the cable and use the trim extend. That will correct itself, and you'll get these trimmed out to the slab edge. So the program will flag those and show them as a kind of a magenta or pink color to represent that problem. And if you went to mesh this, it would flag them again. It would say you can't mesh because the tendon is out of the slab. Okay, that's mapping of a band. Now you can also map using distributed, or you can replicate manually distributed. I'm going to show an example just of mapping distributed. Actually, we actually recommend that you replicate distributed and you maintain, let's say, the spacing. It's probably an easier method to manage the cables, and by manage we mean both throughout the modeling process and then being able to take the data in the program, digest it, and get it into your plans and represent it on your drawings. So if that's if you're not showing each of the cables in your drawings. So you might say for the distributed cable, you might have a range. You might say from this point over to this point, we have so many kips per foot. So in this type of output, you're not drawing every single cable, and it's easier to figure out what this output looks like if all of these cables are consistent in terms of their spacing. So there's different ways to represent the uniform cables. Technically, I could do a banded system in our program. I could actually just map these as banded. You can't build this in some cases, like in the US, but I can model it like this, and then when I go to draw my plans, I just determine what the force per width is for each one of these strips based on a banded. This is a very quick way to model and get results if you're doing like schematic or design development level stuff. So the mapping of distributed cables, let me go to floor design and turn this off, is not it's not dependent on the strips. So actually, I'm going to do one thing here. I'm going to map all of our bands just to have something in here as a reference. So I'll go back to tendon, map banded, just say OK. We have some cables outside of the slab. We'll just ignore that for now. We have our banded tendons in there. Now I want to represent uniform cables. So to do this, I first have to draw in a representative or a primary cable that will be mapped. And I'll go to to tendon. I'm going to add one uniform tendon. So I'll do this down here on this wing. Let's say right here is basically one location where I have a similar tendon that I can map. Once you get above this, in this zone, this is zone 2, you actually add one more span because these two bands split. So you have to add this span here. Okay, and then once you get above that, you might get into zone 3. And then this bumps out, so that creates another zone, and plus there's an opening. This might be zone 4, zone 5, and so on. So you might have several regions where you must create a primary tendon that can be used to map over that region. Here we're showing it for region 1. So if I go ahead and I add a tendon, I'm going to start at the slab edge. This is going to be a cantilever, and I'll use my orthogonal mode. I want the tendon to be aligned straight, and here I just snap in between the two bands. If I wanted to get really specific and really accurate, I could actually click point 1 and 2. That creates a span over the band that you'll have to make straight over that banded line. So this is the second point, third point, and then the fourth point I'll snap perpendicular to the slab edge. So for my primary cable, I'm going to define the properties of this cable. I'm going to assume that for each uniform cable, I'll have 2 strands. The total force will be 2 times the effective force, which is 26.5. And the shape is whatever I define it as. So on one end, we're going to have cantilever down. On the opposite end, we'll also have a cantilever down shape, but I'm going to drop it because it's a short span. It's only 2.38 feet. We'll say this is 3.5. It might be 2. You might have some differential drape there, but we'll say it's straight. And we'll max out the drape with the proper CGs on the 2 interior spans. Okay, so this is the shape of the primary cable. I'm going to take that cable now and I'll go to map distributed. We have a similar input as for map banded, where we input the pre-compression, the percent load balancing. The master span is used for purposes of balance loading. If the spans differ in terms of their tributary width, then we use the master span. We enforce spacing of the tendons 8 times slab thickness, or some user defined. And now when I say OK, the program will indicate select point 1 of 5. It's mapping points 1, 2, 3, 4, and 5 from the primary tendon. So I'll just come down to the bottom end of the range that I want to map from, and I'll say this is point 1, point 2, point 3, point 4, and point 5. And the program fills that in with cables based on our input. Okay, now if I was going to modify, if I wanted to map now into zone 2, I would just take one of these tendons. I would say Control C, Control V to copy and paste it, and I might add this tendon here. And now I can insert a new span. Okay, here's my first high point, my second high point. Notice the low point will shift. And now I could take this tendon and map this distributed also. and that's going to maybe, I'll just say it ends here. So we're going to have point 1, 2, 3, 4, 5, and 6. Something happened. Let's try that again. Map distributed. This is point 1. Let's say point 2, point 3, point 4, 5, and we have 6 points because I added a span, and there's the mapping. Now notice that the spacing between these is different. If we look at the dimension between the two tendon ranges, this spacing here is 4.37. Up here, if I take one of these, it's 4.2. So if we're trying to kind of synthesize this into force per width on our drawings, then you basically have to manage all of the spacings as well as the force per cable or the number of strands per cable. Because if I map 10 different ranges, technically, depending on the loading on the slab, you could end up with 10 different spacings. So a lot of times it's actually easier to just model a cable and then use uniform spacing throughout and just adjust the number of strands as needed when you go through the iterative design process. Okay, so the time is 1:10. I'm going to go about 5 to 10 more minutes. I realize I think we were scheduled for an hour and a half today, but if any of you need to go, I realize it's been over an hour. Please feel free to step out, and I appreciate everyone's attendance. The last thing we're going to look at is the Tendon Optimizer. So I'm going to go over to the model that has the tendons already in it. I'll go over to this model here, and in this model we have banded and uniform cables. So we'll go ahead and analyze. I think this model has 20 pounds per square foot superimposed dead load and 100 pounds per square foot live load. And that was increased just to force an overstress condition. So we'll go ahead and we're going to execute the analysis. And the optimizer was introduced in version 17, Builder 2017. It was introduced to give the users an option for solving issues with stress rather than just trial and error or modifying a tendon and rerunning it and seeing whether or not the stress works. So this works a little bit like the PT recycler. The question is, how do we define bonded and unbonded post-tensioning? Well, the PT is one of the characteristics of PT is bonded or unbonded. So you can specify the type of cable it is using the properties. Here the system is unbonded, and we would just change this to bonded if we wanted to modify the system type. So that's where you would change the type of cable. I mean, typically for a slab on ground that is maybe residential, it depends on where you're at. In the U.S., almost all slab on grounds are unbonded. If SOG is what you're referring to, for slab on ground residential design, even commercial, like for a warehouse, many times here it's unbonded. So let's go ahead and design the sections. So we're designing the sections to see where we might have a stress or a balance loading or a pre-compression problem. This will take just a few moments. Okay, so now we've analyzed and we've evaluated the design cuts. I'll turn our tendons off. And if we go to floor design and I check the stresses, for example, this is for the uniform direction. If I go into the result settings here, and this is for service total condition, under stress, you can see for bottom stress, this says no good. This is actually based on check of all sections, but in both directions. So if I go and I toggle this to the Y direction, we have a few locations where we have overstress. The allowable stress is 424. That's tagged right there. The actual stresses are slightly over. This is for a banded span. And if we want to change the way that this is displayed, we could go to display, allowable stress. Right here we have exceeds only. That will show this value, 424. If I select none and I modify that, notice that it just flags the section as pink. It doesn't color in the graph where it's overstressed. So this exceeds only is a little more informative for the user. If you do all limits, then the program will show you the gray region is here this is like the tensile limit, and then the gray here is the compressive limit, and it shows the values on the screen. So this is even more informative than the previous setting, but we'll go back to the default, which is exceeds only. And if we look at the top stress, we have an overstress here also, 499, 470, allowables 424. This is top tension. Pre-compression in the span, if we look at the P over A, the P over A is okay. And the balance loading, if we look at simplified, is 37. Our program only flags maximum balance loading, so the max is set to 100. Here we're less than 100 obviously, but we can optimize actually to minimum and maximum on both P over A and balance loading. But the main problem we have here is the stress. So we're going to use the optimizer. When we use the optimizer, the program is going to create a virtual tributary that is associated with the selected tendons. And this, we're going to optimize this span here. So the width of the span, I want to pull out the width of this design cut. It's 328 inches. So 27.3 feet, and we'll go into Tendon Optimizer. I need to turn the tendons on. And we'll go back to Optimizer. Anytime you see the yellow square, that means the tendon is optimizable. It can be selected. Once you optimize it and you modify the tendon, then you have to rerun the analysis for it to become optimizable again, because we collect data based on the current state of the tendon. So when I go into the optimizer, I want to change my settings. The first setting, tributary width, we'll come back and fill that in. The next setting is the end section cut. This is a percentage of the span length where virtual cuts A and B are located. We might have virtual cut A here at the end, B is the midspan, and then C is this end. So this distance from here to here is some fraction of the span length defined by this number. The optimizer then allows us to set the balancing. How do we want to balance? Self-weight, super dead. We can report the stress based on a ratio, a factor, or the actual stress. So here you'll notice the ratio is set to 1. The factor, just the coefficient. This is 6 squared of F prime C for tension, 0.6 F prime C for compression, and then the actual gives you the actual value either in PSI or in MPa for metric. We can set up our pre-compressive and load balance ranges for the span we want to optimize. We want to optimize based on service total condition. The criteria we would define as two-way, one-way, or beam. This pulls in the proper allowable stresses. And then we can optimize based on any number of these parameters: pre-compression, balance loading, and stress. Okay, if we go to Optimizer now, we're going to select the tendons that we want to optimize. So I'll select these two cables here, and the program will establish a virtual boundary or a virtual tributary that it's going to optimize for those selected cables. Okay, notice the boundary, the default tributary width is actually equal to, when there are two tendons like this, it's equal to the distance between the end tendons. So like this half of this distance here is taken and added to one side and to the other side. So this tributary is too small for this actual band. The band itself is being used for a tributary that's 27.3 feet. So we need to go back and just update the tributary. I'll update that. And when I update that, the program will readjust the calculation. It itemizes the tendons that are in the tributary. So there's actually two cables here. It's hard to see that because I have the stress diagram turned on top of it. Let me turn off the stress diagram. So there's cables 1 and 2. These are both set to 26.5 for the effective force. The CG is 1. The number of strands is equal to 6, so there's a total of 12 cables in this blue tributary. And under the Optimizer tab, you can see the current total force is set here, 318 kips. It actually meets the pre-compressive range that we set. The load balancing range is slightly less. Okay, so the current load balancing is 49.59. The allowable, or the setting we made, was 50. It's probably close enough. These numbers on the outside represent the force necessary to meet the min and max for pre-compression and load balancing. So our current force is kind of at the bottom end of pre-compression and load balancing, which makes sense because when we mapped it, kind of this is where we ended up. We wanted to meet the bottom end of those two ranges from the mapping. What the mapping doesn't do is it doesn't give you the force necessary to meet the stress control. So what the program is essentially telling us is that in order for us to actually overcome this 2 times top stress allowable, 13% over bottom stress, and 0.2% over end stress, we would have to increase the force to 761 kips. And that shows you the estimation here. That, however, will push us outside the range of pre-compression. That means our pre-compression will be 331 and our load balancing would be 119%, assuming a CG of 1. The stresses would be okay, but we end up failing pre-compression and load balancing. Okay, so based on this information, the user could actually apply this change to the program for the bands, or you could, based on the no good for load balancing and pre-compression, we might actually either have to increase the allowables or assume that we're going to just accept it and then come back and make sure we somehow can rationalize or justify that increase in both of those values. Load balancing, the pre-compression is not a huge issue, 31 psi over allowable or maximum allowable, let's say. Load balancing, we would probably want to check the deflections under sustained load with an 18% overbalance. So if we want to apply the change to this line of tendons for this span, we would apply to model. We could distribute the change over 2 tendons. That's what the distribution is about. The total increase in number of strands is 16.73, so we're going to increase each bundle by 8.37. We could actually assign the modification to a single tendon, either tendon 1 or tendon 2, or we could create a new tendon. We could say the new tendon is going to be basically along all spans where for the two tendons that were selected, or we could use an add tendon. And we would apply that change to the model and rerun the model and update the results. So that's a quick snapshot of the editor, or excuse me, of the optimizer. We're going to go ahead now, and I'm going to have to stop there. There's another meeting coming up, but at this point, I'll take any questions that you have relative to what we've discussed today. Marcus, so do we have to enter the tributary width manually? Yes, because the default for a banded system will be defined just as I've shown it. Other questions? I have about 5 minutes for questions if anyone has anything. All right. No questions today, so if there are none, I'll just go ahead and thank everyone for joining us today. The meeting will be placed on our YouTube site. There's been some issues with that site, so we're still trying to get some from our specific page there. We're still trying to get some of the videos from the last two sessions uploaded, but we'll get those soon enough. And if you have any questions that may not have been asked today, feel free to contact us, and you can always contact support at AdaptSoft, and we'd be happy to help in that environment also. All right, thanks everyone. Have a great afternoon, and we'll talk to you soon.